So let's continue and go to the second exercise. There we are going to use the Ziegler-Nichols closed loop technique. Here with the open loop technique, the problem that this can be used for systems with low order. So if you have a very high order system, this will not work. In the closed loop, what we will do that we'll bring the system in a quasi-stability mode. So when we have steady state oscillation, here the limiting factor, not every system can be brought to this limit. So let's start. Setup is the same. We have a controller which is 1, sensor which is 1, and we have the system. This is in this form, and what we can do, we can just do a simple serial connection of these three terms. So transfer function, transfer function, transfer function. The first is 1 over s. Of course, there are multiple ways to do this. I will show the simplest one. Then we have s plus 1 and s plus 2. Okay, we excite this system with step. We start at 0 time instance. Voila. And I check the output like this. Click on the scope. Okay, I choose a higher time instance. We can see, okay, this system doesn't look so stable. The next step is that we have to make this closed loop setup. I remove this and I add here an add block. You can use some block or whatever you like, plus minus. This I connect back to the output. And for this setup, I go back here. So in this document, what you can see the closed loop technique. What we have to do that we use here again, we start from 1 and we tune this gain until we see oscillations like this. So I add here again. I move these blocks a little bit. And we can use, for instance, a gadget to do this tuning of the gain. Here I clicked on library browser, Simulink, and here we have dashboard, and you can look around. We have many types of gadgets. Feel free to discover these. I'm going to use the knob gadget. Here I double click. I have to choose the item what I want to do, what I want to change. This is the gain. I connect it, apply, and we can play around. Show the scope figure. This looks like this. Stable. Okay, let's try a much higher value. It looks promising. So we can see that it's already unstable. Of course, the size you can change yourself, whatever it's comfortable for you. So this you can integrate with other tools from other projects. Let's see, this value is still not good enough. This looks already much better. Okay. And you can play around. We should have steady state oscillation. I can go higher in time domain and see what happens. Okay, as you can see, it's a little bit too much because in higher terms, it's going to go higher. So let's try 6. A little bit higher. playing. If you don't like these gadgets, you can also manually change here again. So here we have at the moment 6.2. I can try 6.5. This you will do also in the next labo exercise. So 6.5 was too much. I try 6.4. Try 6.3. 6.1 looks better. 6.05. We are getting there. 6.1. It looks good. Okay. So we had to determine what is here the K value. Is the critical gain when we bring the system to the limits of stability. And the next step is to read here the period time. For this, I advise that you can decrease the stop time like this, and we can use also cursors. So here we have triggers and measurements, and we can use, for instance, cursor measurements. I select the two peak values. Yes, here and here. You can see here the values as well. So the period is here. The length of the period is 4.46 seconds. So I can make also text here. Crit was 6.05. I will read back. P crit is 4.46 around. Oops, it didn't read. So I use the text field again. So P crit 4.464 second. K crit is 6.01. Okay. So we have these two parameters, and then we can do the PID controller. I am a bit lazy, so I will just copy paste this. I don't need a second gadget. Like this. I can also hide these blocks, create subsystem form section, because in practice you don't know the exact values of this block. You have to measure, and here we do simulation of a measurement. And I will use the PID structure given here. So we will start with the gain, what I calculate here, integration and the diff time. So I open here the loop. I add an add block. Of course, you can use any other block. Okay, I connected this. Then we need an integrator, transfer function, like this. I copy, I connect these blocks like this. Okay, let's set up the E term. So we use this format 1 over time times s, 1 over times s. So the time here we can read. It says the period, critical period over 2. So it's 4.46 over 2. I can make it larger. Voila. Then here we have the div block. Again, this ideal div block we cannot realize, but we can realize a combination of this plus a low pass filter. With the low pass filter, we will not amplify the noise. Okay, that is also an advantage. So let's do so. And here we see the TD, tau D, is pre-crit over 8. So the critical period was 4.46 over 8. Excellent. And here we usually put 10% of this time constant. So 0.446 over 8. So again, it's a combination of the ideal term here plus a low pass filter. And the last part is this gain factor here. And here we will use 60% of the critical gain times the 6.01. And the scope, yeah, we can add the second input. Here's number of input ports, or let's use 3 inputs. So this I will call as output. Then here we will have the desired value, the set point, or the reference signal, set point, and this is here the error after the junction point, error. And we can show the measurement. And we see that something is not correct. Like this. So now we have to think about what went wrong. We have here our system. We have here our feedback. And we have the integration time here and the differentiation time. And what we can do, we can debug. So what happens if I remove this block and I simply make a PI system? In this case, I have to reread the parameters. For instance, here I have to take 45% of the critical value. Yes. And here I have to take, instead of over 2, I have to take over 1.2. And we have to check what is now at the output. And we see, it's so something is with this differentiator. We can also play here around, as you will do in a practice, what happens if I now change this gain value. So instead of 45%, I take 35%. Then I go, I can see that I decrease again this value, then I will have less oscillation. Then I go here, and again, decrease the volume. It starts to look nice. So this is also how you will do in the next labo session. Okay, so we see that this we could make stable, so there was something with the differential term. For this, we can think two possible faults. First of all, maybe this low pass filter was incorrectly selected, or there is something with this diff term. So what we can do, we have different blocks. For instance, we can use the difference here. The problem that we have the discrete time version of this block, and if you are not sure that what are the available blocks, you can just go here and look around. And here we have mass operations. You can find anything from integration, subtract. So for instance, for this block, instead of using the add block, you can use also the subtract block. You have a very, very large freedom to operate. Okay, it's always just look around what are the possibilities. Then we have continuous blocks. Here are the most of the systems, and you can see that from here we use the transfer function. Now I can try to use a derivative function which will approximate this td times s function. I place it here, I connect, and I will use here a gain value to adjust the differentiation time, like this. Oops. So now it operates as, like here you can see, it's an approximation. I go back to the table and I play around again. So integrator worked, we saw it, I can enlarge it. This was the previous setup. From the PI, we will go back now to the P setup. So instead of multiplying with 1.2, I divide with 2. Then I go here and I play also around. So here I see that this should be the critical period over 8. So it's 4.46 over 8. And we have to change again the K value. Start with the recommended 0.6 times the critical gain. And we look at the output, what happens now. And we see, aha, it works. And it works very good. You can see that it's much faster than before. So this means that the error what we made was in the definition of the low pass filter. So this is basically how you debug here. And of course, now it's not necessary to show this 100 second. So it's better to show till we reach the steady state moment. And this I changed to 20. And voila. And if you forget them, what are these notations, then you can just view legend. And this is our desired value. This is the output, and the difference between two is the error. Let's see that here we have a temperature, room temperature, and I want to control the room temperature. And the desired value is 30 degrees. Then we can look what would happen in reality. And we see that indeed this PID controller makes the error 0. So, and we have here oscillation, and we can, for instance, play again with this K value to change this oscillation. Maybe this 60% is too much. Try 50%. Again, I go here and I play around and so forth. So this is what you will have to do in the next VPO session when we will have a ping pong balancing exercise. Okay, thank you for your attention. Please play around. You can find all the solutions for the PI and PID on my website. Okay, thanks.